Synchronous motor controllers. In this presentation, we're going to be looking at methods of starting a synchronous motor. What do synchronous motor controllers need to do? Old synchronous motor controllers and new synchronous motor controllers. There are two main methods of starting a synchronous motor. The first one is to use a pony motor to bring the sync motor up to speed prior to synchronizing it. The other method would be to embed an armature winding in the rotor, allowing for self-starting when the stator winding is energized. Pony motor assist is typically done with much larger apparatus. The skim motor, or whatever the prime mover is used to start the synchronous motor that does not have an armature winding. When the percent slip has been reached, that is the value that's required prior to syncing, the synchronous motor is synchronized to the stator field. The skim motor is then de-energized and or decoupled from the synchronous motor via a clutch system. The more common application that we see and what our controller circuits are going to focus on is an armature winding in a synchronous motor, making it inherently self-starting. The stator winding is energized. The armature winding allows for the rotor to start turning. It must be started with no load, and the armature brings the rotor up to percent slip that is required. Once the field coil is energized with DC, the unit is then synchronized, and because of that, no current will flow in the armature winding because there will be no lines of flux being cut. Synchronous motor controllers have three roles. They must be able to start the motor by energizing the stator. They need to be able to synchronize the rotor when the slip is between 3 to 5%, and they need to be able to de-energize the entire assembly if mechanical load pulls the rotor out of synchronism, also referred to as pull-out torque values. There are three common types of synchronous motor controllers that we're going to look at. The first one is a very basic example. It's a manual push-button operation. Then we're going to look at an old automatic synchronous motor controller and a new automatic synchronous motor controller. This is an example of a manual push-button synchronous motor controller. On the left-hand side in black, we see this is controlling the stator and the three-phase stator field. When start is pressed, the stator is energized with three-phase, and the armature winding will have current or voltage induced into it. Current will flow, and it will cause the rotor to start turning. Now, this particular system is manual because on the right-hand side, we also have a set of push buttons, an off and a run. The blue circuit is where the DC field coil is located, and by pressing the blue run, normally open push button, we would energize the field coil with DC voltage. Now, this, of course, is not extremely advantageous because it really is dependent on the user to know exactly when the correct time is to synchronize the field. We're going to take a look at the parts and their purpose and the full operation of this older style of synchronous motor controller. And while we're looking at it, it's important to remember that as the synchronous motor is brought up to speed, the rotor voltage and frequency will decrease as the rotor increases in RPM. So just keep this diagram in the back of your mind. Here's the full schematic of a basic, older style synchronous motor controller. We're going to focus on some of the more odd or unique components in this circuit to get an idea of how some different systems will operate. The first one we're going to look at is the field contactor. Now, the field contactor is shown here. We have a coil and 3 contacts. It is rated for DC, but what makes it unique is the way in which it articulates or changes the contact states. They don't all change at the same time. The purpose of the field contactor is to ensure that the field coil of the sync motor is never open circuited. During start, we have the discharge resistor connected into the DC field. And we can see if we trace the line all the way down through this section, the discharge resistor is connected into the field winding. When we're going to synchronize, there's a transition, and this is called a make before break setup. And what it means is that it applies DC voltage to the field winding at the same time that the discharge resistor is still connected. This is a make before break. Finally, when the motor is fully synchronized, it opens the field contactor or full field contact for the discharge resistor. And so there's an overlap between the two DC supply contacts and the one discharge resistor contact. Make before break, thereby ensuring that the field coil is never open circuited. Another item is this, it's a reactor. The reactor is just an inductive coil. As the rotor speed increases during start, the frequency of the AC voltage induced into the rotor will decrease. This will reduce the XL of the coil, allowing more current through it. So kind of an interesting application. The voltage across the reactor and the DC PFR coil, which we're going to take a look at in a few moments, will decrease. So when we first start the motor, we have a fairly high hertz and high voltage, and that means that there's a significant value of XL in the reactor because the XL of an inductive coil is very much dependent on not only the henries, but also the frequency. As the frequency starts to decrease and the voltage decreases, more current will flow through the reactor. Now, because the reactor and this coil are both in parallel, it means that they must have the same voltage. And if more current's flowing through the reactor, the voltage drop across the reactor will become less and less. The next item is called a polarized field frequency relay. Now, this is a quirky piece of kit, and that's because its purpose is to synchronize the rotor to the stator when the percent slip is near zero. It's a mechanical two-coil relay. In this relay, we have a DC coil and an AC coil, and one normally closed contact. The DC coil is located down here and is supplied by the DC source, which is going to be used to energize the field coil to synchronize this synchronous motor. The AC coil is connected right there, and it's below the reactor. Now it's going to be supplied by the field winding as the motor is starting up. Because remember, when we first start the synchronous motor, we are going to have AC voltage induced into that field. When a sync motor is starting, so before synchronization, an AC voltage will be induced into the rotor winding due to the difference in RPM from the stator. The two-coil relay is designed to energize the field coil with DC at exactly the right moment by using magnetic flux developed in the AC and DC coils. Let's take a look at how that's done. The purpose we see here when the sync motor is starting, in one of the alternations, my magnetic flux from my AC coil will oppose. In one alternation, the magnetic flux in the AC coil will aid the DC coil magnetic flux. So let's take a look at how this happens. When we are going through the negative alternation, we can see that it is aiding, so increasing. You could think of it as the AC and the DC are traveling in the same direction, which means the total magnetic flux is greater. When it's in the reverse direction, it is opposing. And as the motor is gaining speed, the difference between the stator and the rotor RPM will go down. And this will then result in a lower voltage being induced into the rotor windings. At a certain point, the amount of total resultant flux will be insufficient to hold the armature of this relay in place. Now it's finely tuned so that it is released at precisely the right moment. So now that it's released, the PFR contact will close. and this will energize the field coil of the synchronous motor with DC. On the next positive alternation, the field coil will then seamlessly synchronize with the stator. Another one of the quirky items that we have in a synchronous motor controller of this era is called an out-of-step relay. The out-of-step relay is a very low ohm value coil and a single, normally closed, contact. The out-of-step relay is essentially a current-operated timer relay. Its purpose is to de-energize the motor if the starting synchronous time is too long. If the startup time exceeds the preset time, the relay will shut off the motor by opening the contact. When starting, current flows through the out-of-step relay coil. The timer function starts much like a TDOE. If the starting sequence takes longer than designed, the relay contact opens and the motor is de-energized. Let's take a look at the full operation. This is how everything starts. The DC PFR coil is energized. The start push button is pressed and CR1 coil energizes. CR1 contacts all change state or close, which then results in not only the motor stator being energized, but the M coil being energized also. At this point, AC voltage is induced into the rotor because we have a rotating magnetic field. The PFR armature is pulled in because of this AC voltage, and the contact opens. As we can see here, the PFR contact is now open. The M contacts close, and the holding path is established across the start push button. Now the rotor AC voltage and frequency will drop, and the inductor or reactor will start to shunt current across the PFR AC coil. And we know that this is going to decrease the voltage across the AC coil. And we know the purpose of doing that is to release the armature at exactly the right moment. The AC PFR coil voltage is now low and the armature is released. The PFR contact closes, and that's going back to its original normal state. At this point, the field contactor coil is energized, and it is going to first close the two DC contacts that are going to energize the field coil with DC voltage. After that, it is going to then open the field contact for the discharge resistor. So at this point, my rotor is now synchronized to the stator field. The DC contactor is now going to open and break the contact to the discharge resistor, and my motor is now running in a fully synchronized condition. A new automatic type synchronous motor controller looks more like this. And there's a lot of electronic magic that takes place in behind these fancy enclosures. Essentially, it will monitor everything, it'll start, and it will synchronize. Not only that, it'll also control for power factor correction if required. So this is probably more realistic for what you may encounter in the field for a new installation. However, the older style of synchronous motor starters do exist out in industry still.